Okay, let's unpack this. Have you ever looked at the periodic table and thought, beyond just where they sit, what truly makes each group of elements unique? And how do those tiny atomic differences dramatically dictate their entire personality? I mean, from exploding in water to forming the backbone of life, or even subtly influencing human history. Today, we're taking a deep dive into Chapter 20 of Zumdahl, and DeCoste's chemistry, the representative elements, our mission, to really uncover these surprising destinies, showing you how their atomic quirks dictate pretty much everything around us.
Indeed. And we'll be connecting the dots between things you've already learned, like valence electrons, atomic size, that sort of thing, and this really rich tapestry of chemical properties. Expect some aha moments, I think, as we explore the surprising similarities and the crucial differences that make these main group elements so vital and fascinating. And we'll do it all without a single visual, just your imagination and our guiding voices.
Okay, so as we start this journey into the representative elements, the main group elements, what's the fundamental characteristic? What defines them?
Well, we start with their core identity. Their chemical properties are primarily determined by their valence level s and p electrons. These are the elements in groups 1A1 through 8A18 on the periodic table. And within these groups, you'll see that classic trend of metallic character increasing as you go down. They become more like what you typically think of as a metal.
Right, that makes sense for the overall trend. But I'm curious, are there any general rules that seem to get, well, broken when we look at the very first element in each group? It seems like there are often pretty dramatic differences there.
That's a fantastic observation and absolutely key. The first member of a group often behaves quite differently from the rest. And it largely comes down to atomic size, just how big the atom is. Take hydrogen in group 1A1, for instance. It's a nonmetal. It forms covalent bonds, totally unlike lithium right below it, which is a very active metal. Or consider beryllium in group 2A2. While most group 2A oxides are basic, beryllium oxide is, well, it's amphoteric.
Amphoteric. Okay, what does that mean for how it actually behaves?
It means beryllium oxide can act as both an acid and a base, so it reacts with strong acids and strong bases. This unique behavior, it really stems from the beryllium ion, B2 plus log, being so small and highly charged. This small size effectively polarizes oxygen's electron cloud. It pulls on it, giving its bonds more covalent character compared to the more ionic oxides of the larger group 2A metals down the column.
Ah, I see. So that subtle difference in size isn't just a factoid, it's like a fundamental fork in the road. It explains why beryllium kind of steps away from its group's typical behavior. And I imagine that small size also affects how elements form bonds too, right? Like the huge differences we see between carbon and silicon in group 4A14.
Exactly. This is a really profound divergence that comes from a single periodic table trend size. Carbon's chemistry, which is the basis of all life, it's dominated by its ability to form strong chains of CC single bonds, but critically also robust pi bonds, double and triple bonds. Think of carbon dioxide, CO2. It's a discrete molecule, little individual molecules with strong double bonds. But silicon, being larger, just doesn't form strong pi bonds as readily. It's not good at it. So silica, SiO2, the main component of sand and rocks, is instead based on this extensive network of SiO single bonds forming tetrahedra all linked together.
Oh. So that one fact, the ability or inability to form strong pi bonds, means carbon builds the flexible, complex molecules of life, while silicon builds the rigid, extended networks that literally make up the ground we walk on and the chips in our phones. That's a truly powerful connection from, well, one simple principle.
It truly is. It really makes you realize how fundamental atomic size and bonding preferences are. Now, you might be wondering, where do we actually find these elements and how do we get them in their pure form?
Yeah, because the Earth's crust, oceans, and atmosphere has a very different elemental mix than, say, the human body. Oxygen is just overwhelmingly abundant everywhere, especially tied up in water and minerals. Silicon's number 2 in the crust, sand and rocks. And the most abundant metals are aluminum and iron, usually found in ores combined with nonmetals, very often oxygen.
And then in the human body, it's a totally different story. Oxygen, carbon, hydrogen, and nitrogen, they form the backbone of life. Even trace elements like zinc found in over 150 biomolecules are absolutely crucial for us. Now, when it comes to getting pure metals from their ores, it's almost always a reduction process. We call it metallurgy, often uses carbon as a cheap reducing agent. Or for very active metals, you need electrolysis. Non-metals like nitrogen and oxygen, they're commonly obtained from the liquefaction and distillation of air, just separating them based on their different boiling points. Sulfur, for instance, that's recovered from underground deposits using the Frasch process. It basically melts it underground with superheated water and then pumps it up. And the halogens, group 7A, they're generally obtained by oxidizing their halide anions, the negative ions.
Before we move on, I just love how chemistry connects to really unexpected fields. We have a great example from our source material. Linda Van Hart, an artist and metalsmith. Her whole career involves using chemical methods for soldering, polishing, creating surface coloration on metals. It's just a fantastic reminder that these chemical principles aren't just in textbooks, they're everywhere, even in the intricate beauty of art.
Well,
Okay, so from these broad principles, let's start our journey through the individual groups. Let's kick off with group 1A1, the alkali metals. What makes them so famously reactive?
right. These elements, they all have that single NS1 valence electron, and they are incredibly keen to lose that electron. They want to form M plus stations, positive ions, to get a stable, noble gas electron configuration. And we've probably all seen videos of their vigorous reaction with water produces hydrogen gas and often quite a spectacular show. Bang.
And speaking of that reaction, I remember learning something that seemed a bit counterintuitive. Lithium is the strongest reducing agent in water, meaning it should react most readily, yet it actually reacts more slowly than sodium or potassium. That's a fascinating twist. What's the underlying reason for that?
It's a beautiful example of thermodynamics versus kinetics. These two aspects of chemistry can sometimes seem to pull in opposite directions. The thermodynamics of it, the sort of driving force, says lithium wants to react very strongly. Why? Because it's small. Li plus ion has a very high hydration energy. That means it releases a lot of energy when it gets surrounded by water molecules. Makes the formation of Li plus really thermodynamically favorable. However, the kinetics, the actual speed of the reaction, is slowed down. Lithium has a higher melting point than sodium or potassium, so it doesn't melt and spread out on the water surface like sodium or potassium do. This limits its contact area and just slows down the rate of the reaction. It's like having a really powerful engine, thermodynamically speaking, but it's stuck in first gear kinetically.
That's a great way to put it. Thermodynamically favorable, but kinetically hindered. Got it. And of course, we can't forget Na plus and K plus ions are absolutely crucial biologically, right? For nerve and muscle function, with those carefully regulated concentrations inside and outside our cells.
Absolutely essential. Now, let's consider hydrogen itself. It's often put in group 1A, but it really is unique.
It truly is. Sometimes it feels like it deserves its own little box on the periodic table, which makes sense given its simple structure, just one proton, one electron.
Precisely. It's a colorless, odorless, highly flammable gas, and it forms three main types of hydrides, compounds with hydrogen. First, you have ionic hydrides with active metals. These contain the H ion, the hydride ion, which is a very strong reducing agent. Then there are covalent hydrides formed with nonmetals. Water, H2O, is the prime example. Its polarity and hydrogen bonding give it all sorts of unusual properties, like ice being less dense than liquid water. And finally, you get metallic or interstitial hydrides with transition metals. Here, hydrogen atoms literally occupy holes in the metal's crystal structure. Palladium, for example, can absorb something like 900 times its own volume of hydrogen gas. Makes these materials interesting for potential hydrogen fuel storage.
Okay, so from these very reactive alkali metals and unique hydrogen, let's start moving across the periodic table. What's the standout story in group 2A2, the alkaline earth metals?
Well, these elements are also very reactive. Not quite as much as group 1A, but still very reactive. They readily form M2 plus characations, losing 2 electrons. Their oxides are generally basic, hence the name alkaline earth. We did mention beryllium's amphoteric oxide earlier, that's the exception, but for the most part, they're basic. Calcium and magnesium, in particular, are biologically essential. Calcium, obviously, for bones and teeth. Magnesium is vital for metabolism. Hundreds of enzymes rely on it. And these elements are also responsible for hard water.
Ah, hard water. Yes, the bane of our detergents and the reason for that crusty lime scale in kettles and pipes. How does ion exchange solve that problem, giving us soft water?
Ion exchange resins are actually pretty ingenious polymers. They have these built-in ionic sites specifically designed to grab hold of those hard water ions like Say2 plus and Mg2 plus Say. And in their place, the resin releases harmless, soluble sodium ions, Na plus I. So it effectively swaps out the problematic ions, softening the water.
That's a really neat example of practical chemistry solving an everyday problem.
Oh.
Okay, let's keep moving across. What happens as we reach group 3A13?
Here, we definitely see that trend of increasing metallic character as you go down the group really clearly. Boron, sitting at the top, is a classic nonmetal. It forms these unique covalent hydrides called borenes. These are incredibly electron-deficient compounds, very reactive. So much so, they were actually evaluated as potential rocket fuels back in the day. Moving down, aluminum, while it's definitely a metal, still shows significant covalent character in its bonds to nonmetals. And its oxide, like beryllium's, is also amphoteric. And then there's gallium. Gallium has this remarkably low melting point, just 29.8 degrees Celsius. You can literally melt it in your hand. But it has a very high boiling point. This combination gives it the largest liquid temperature range of any metal, which makes it useful for some specialized high-temperature thermometers.
Okay, from the diverse properties of Group 3A, we move to Group 4A14. This brings us to two absolute giants, carbon and silicon. We touched on them earlier, the elements that essentially form the foundations of life and geology.
Absolutely. And beyond their differences in pi bonding ability, this group beautifully illustrates that transition.
Yeah.
Non-metal, carbon, to semi-metal, silicon, germanium, down to metal, tin, lead. We see carbon in its fascinating allotropes like graphite and diamonds, and the newer forms like fullerenes, buckyballs. Tin has this curious phenomenon called tin disease, or tin pest, where it literally crumbles at low temperatures because it changes from one crystalline form, white tin, to another gray tin. And then there's lead.
Lead. And speaking of its impact, lead's toxicity has this long, grim history, doesn't it? Even potentially linked to the fall of the Roman Empire. And our source materials has that fascinating chemical connection about Beethoven, which really brings this historical impact home.
Indeed. Lead poisoning, it's been known since ancient times. The Romans were exposed through lead plumbing, lead cups, and even sweeteners like sapa, that was a syrup made from boiling grape juice in lead-lined vessels. And centuries later, the analysis of a lock of Beethoven's hair showed lead concentrations something like 100 times normal levels. It potentially explains some of his notorious volatile temper and his chronic illnesses. It's just a stark reminder of chemistry's profound, sometimes negative impact, even on major historical figures. Today, lead's main use is in lead-acid car batteries, but its toxic legacy persists, especially concerning old lead paint in houses.
Lead's dark historical footprint is definitely a sobering reminder of chemistry's power. Okay, shifting over to Group 5A15, we find elements that seem capable of almost anything. They can be life-sustaining, but also incredibly explosive. What's driving this versatility?
This group truly shows a wide range of properties. Nitrogen and phosphorus at the top are nonmetals. Antimony and bismuth further down are more metallic. A key difference, maybe the key difference, is nitrogen's unique ability to form very strong pi bonds, specifically that triple bond in N2. That's why elemental nitrogen exists as this incredibly stable diatomic N2 molecule. The other elements in the group, like phosphorus, they're larger. They don't do pi bonds well, so instead they form larger aggregates with single bonds, like the P4 tetrahedron structure you find in white phosphorus.
And that stability of the nitrogen N2 molecule, it's almost legendary for its unreactivity, right? Which paradoxically has some pretty explosive consequences.
That's precisely it. That triple bond is incredibly strong, 941 kilojoules per mole, to break it. This means that most nitrogen compounds are actually thermodynamically unstable compared to forming elemental N2 gas. So they have a strong tendency to decompose, often exothermically, releasing huge amounts of energy and gas very rapidly as they form stable N2. This is the driving force behind almost all conventional nitrogen-based explosives, like nitroglycerin, TNT, dynamite. But that extreme stability of N2 also makes it incredibly difficult to convert atmospheric nitrogen, which is mostly N2, into usable forms like ammonia for fertilizers. That process is called nitrogen fixation.
Right. So on one hand, it's this super stable, almost inert gas that makes things explode violently. And on the other, it's essential for all life, but it's locked up tight and hard to access chemically. This brings us to the famous Haber process, doesn't it?
Yes, the Haber-Bosch process, manufacturing ammonia directly from nitrogen and hydrogen for fertilizers. It's a classic chemical engineering case study in balancing kinetics and thermodynamics. You need a high temperature to get a reasonable reaction rate, but the reaction to form ammonia is exothermic, so high temperature actually shifts the equilibrium away from the product you want. Bad thermodynamics. So a compromise is found. Moderately high temperature, very high pressure to push the equilibrium forward, and crucially, a catalyst to speed things up. Of course, natural nitrogen fixation also occurs, lightning does a bit, but mostly it's done by specialized nitrogen-fixing bacteria, often living in nodules on the roots of plants like legumes, and they do it much more efficiently at room temperature and pressure than the Haber process.
Fascinating. Ammonia as the product of nitrogen fixation is obviously crucial. What about some of its other interesting applications, or maybe those of its close chemical relatives?
Well, ammonia itself has that pyramidal structure and extensive hydrogen bonding, which gives it a surprisingly high boiling point for such a small molecule. Then there's hydrazine, N2H4. That's another interesting nitrogen hydride. It's a powerful reducing agent. It was famously used as a rocket propellant, part of the fuel mix for the U.S. Space Shuttle orbiter engines, for example. It's also used industrially as a blowing agent to create porous plastics and foams. Then we have the nitrogen oxides. There's N2O, nitrous oxide, better known perhaps as laughing gas.
Nitrous oxide. That has some truly wild applications beyond just the dentist's office, right?
It certainly does, yeah. Beyond its historical use as an anesthetic and its current role puffing up whipped cream from a can, it's actually used by some street racers. They inject it into engines for a burst of instant horsepower. It works partly because it decomposes to provide extra oxygen and partly due to its cooling effect on the intake air. Unfortunately, it's also a significant greenhouse gas. Other key oxides include nitric oxide, NO, which is an important biological signaling molecule, and an odd electron molecule, which makes it quite reactive, and nitrogen dioxide, NO2, which is a component of photochemical smog, and finally nitric acid, HNO3. That's a huge industrial chemical produced by the Ostwald process. It's essential for making fertilizers and, again, explosives.
Okay, now let's compare nitrogen to its neighbor just below it in group 5A15, phosphorus. You mentioned it earlier, but its chemistry seems surprisingly different.
The differences are really stark, yeah. And again, it mostly comes down to phosphorus being larger, having lower electronegativity, and having accessible d orbitals for bonding. Crucially, this means it doesn't form strong pi bonds like nitrogen does. Elemental phosphorus comes in several different forms, or allotropes. There's highly reactive white phosphorus, which consists of individual P4 tetrahedral molecules. It's pyrophoric, meaning it ignites spontaneously in air, and it's highly toxic. Then there are the less reactive red and black forms, which are polymeric networks. Phosphorus oxides, like P4O10, are incredibly powerful dehydrating agents. They rip water out of other molecules. And they form crucial oxyacids like phosphoric acid, H3PO4, which is vital for fertilizers and found in soft drinks.
Okay, let's move over to group 6A16, starting with oxygen itself, the most abundant element in and near the Earth's crust.
Right. Oxygen exists primarily in two elemental forms, the familiar O2 molecule we breathe and ozone, O3. What's truly fascinating about O2, and something that simple Lewis structures don't predict, is that molecular orbital theory shows it actually has two unpaired electrons. This makes O2 paramagnetic. And this isn't just some textbook detail, it's a critical insight that explains its unique reactivity and why it's so fundamental for cellular respiration. Ozone O3 has this unique bent structure. It's a very powerful oxidizing agent used for water purification and sometimes washing produce, as it doesn't leave toxic residues like chlorine can. And critically, the ozone layer high up in the stratosphere absorbs most of the harmful high-energy UV radiation from the sun, protecting life on Earth by converting that dangerous energy into harmless heat.
And oxygen's neighbor, sulfur, also has a really rich and industrially significant chemistry.
It does. Sulfur is found in large underground deposits, often near salt domes. It's recovered by the Frasch process, which involves pumping superheated water down to melt the sulfur, and then using compressed air to force the molten sulfur up to the surface. Like phosphorus, sulfur prefers to form larger aggregates with single bonds rather than pi bonds. The most common form contains S8 rings, found in different crystalline structures called rhombic and monoclinic sulfur. Its oxides, SO2 and SO3, are really significant. SO2 is used as an antibacterial agent for preserving fruit, for example, and SO3 reacts violently with water to form sulfuric acid, H2SO4. Sulfuric acid is often called the king of chemicals. It's manufactured in greater amounts than any other single chemical worldwide, absolutely critical for fertilizers, refining petroleum, making detergents, and countless other processes. It's also a powerful dehydrating agent, famously demonstrated by pouring it on sugar, which turns into a steaming black mass of carbon.
Wow. Okay, finally, let's head over to group 7A17, the halogens, famously reactive nonmetals.
Yes, these are all highly reactive nonmetals. You generally find them in nature as halide ions, F, Cl, Br, I. Their electronegativity values are very high. They really want to gain an electron. When they react with hydrogen to form the hydrogen halides HX compounds, we see an interesting anomaly again. Hydrogen fluoride, HF, is actually a weak acid in water, unlike HCl, HBr, and HI, which are all strong acids.
That seems backwards, doesn't it? Fluorine is the most electronegative element. You'd think the HF bond would be easiest to break in water, so it's not just about bond strength there. Something else is at play.
Precisely. It's a bit counterintuitive. While the HF bond is very strong, the main reason HF is a weak acid has to do with entropy, specifically the entropy of hydration of the fluoride ion. The small F ion exerts a very strong ordering effect on the surrounding water molecules. Think of it like this. The tiny fluoride ion is so good at pulling water molecules tightly around itself that they become rigidly organized, almost frozen in place. This strong attraction releases a lot of energy. That's a favorable high hydration energy. But creating all that order actually reduces the overall randomness or entropy of the system significantly. This unfavorable entropy change makes the overall process of dissociation less favorable than for the larger halide ions. Hence, HF acts as a weak acid.
That's subtle but makes sense. It's about the whole system, including how the water behaves.
Okay.
What about other halogen compounds?
Well, hydrochloric acid, HCl, is hugely important industrially, and it's also the acid in our stomachs. Hydrofluoric acid, HF, despite being a weak acid, is famously used to etch glass because it reacts with the silicon dioxide in glass. The halogens also form a whole series of oxyacids where they're bonded to oxygen. A common example is hypochlorous acid, HOCl. This is the active ingredient formed when chlorine dissolves in water, and it's a strong oxidizing agent used in household bleaches and disinfectants. Its formation involves a disproportionation reaction, where chlorine atoms are simultaneously oxidized to +1 in HOCl and reduced to -1 in Cl.
Okay, that brings us to our final stop on this tour, Group 8A18, the noble gases. They were once thought to be completely inert, right, totally unreactive.
Indeed. For a long time, that was the dogma. These elements, with their completely filled s and 4 valence orbitals, seemed perfectly stable and unwilling to react with anything. They were called the inert gases. But in 1962, Neil Bartlett, working at the University of British Columbia, famously synthesized the first noble gas compound, ISOP-TTF6. He realized xenon's ionization energy was similar to oxygen's, and he'd already made O2 plus PTF6. This proved they weren't truly inert, just relatively unreactive, noble, you might say. While helium and neon still don't really form stable chemical compounds under normal conditions, though they have crucial uses, like liquid helium as a supercoolant or in blimps, and neon in those iconic electric signs, the heavier ones, krypton and especially xenon, being larger with more easily perturbed electron clouds, form many stable compounds, usually with highly electronegative elements like fluorine and oxygen. Examples include xenon tetrafluoride, XF4, and even the dangerously explosive xenon trioxide, XeO3. It's really a testament to how even the elements we think are the most stable and predictable can still surprise us under the right chemical conditions.
What an incredible journey that was, through the representative elements. Seriously, from hydrogen's unique position all the way over to the noble gases defying their inert reputation. We've really seen how fundamental properties like atomic size, electronegativity, and bonding preferences dictate just about everything. We've uncovered the chemistry behind explosives, fertilizers, hard water, water purification, semiconductor technology, and even potentially a famous composer's health struggles centuries ago.
It really does highlight that chemistry isn't just abstract formulas on a page, is it? It's about understanding this intricate dance of atoms and electrons that literally shapes our world. From the microscopic atomic level right up to the macroscopic things we see and use every day. Every element, every group plays its critical role with its own distinct chemical personality.
So, what does this all mean for you listening in? As you continue your studies in chemistry, try to remember that these principles are all interconnected. When you see a chemical reaction or learn about a specific property of an element or compound, don't just try to memorize it. Ask yourself, okay, how does its position on the periodic table, its size, its electron configuration, or its bonding preferences explain why it behaves that way? Finus. That curiosity, asking why, is really your shortcut to truly understanding the material and becoming genuinely well-informed.
Absolutely. Next time you encounter a new element or compound, think beyond just its name or formula. Consider the story its valence electrons are telling and the real-world impact that story has. It's truly a deep dive that keeps on giving. There are always more connections to find the more you look.
Well, thank you so much for joining us on this deep dive into the representative elements.
Yeah.
We really hope you feel a little more connected to the amazing chemistry that surrounds us every single day. Until next time, keep exploring.